Hi, this is week 2. It's the day after Easter, so if you hear me and I'm not quite audible, it's because I'm eating a peep or something like that, some leftover candy while we're talking. But I'll try to get through this audibly. All right, so here are some notes at the front, right? We have Zoom, remember Monday, Wednesday, Friday, SI, Monday, Wednesday. Those are both on Blackboard. Also, there's tutoring. It'll be online. I have some more information on the next page. This week we're going, or this week we're going to go and continue on thermodynamics. Zoom is going to be used for office hours. Homework number 1 through 3 are due Monday, Wednesday, Friday. So make sure you're getting through those. The 1 through 3 are all on Sapling. Next week, April 20th through 24th, we'll actually move on to kinetics, our next step. This won't be on the first test. Zoom, you can see next week's going to be a little bit different. Office hours, one will be a quiz. I'll talk more about that. And then Friday will be a review. Homework 4, that's the one for this lesson, will be due on April 20th at 11:59 p.m. This is through Blackboard. I'll talk more about this at the end. Homework 5 and 6 will also be due next week. And then April 27th is our first test. It's going to be on lessons 1 through 6. Okay, so here's some review. Last time we talked about standard enthalpy of combustion and formation. Make sure you know those key terms. One is burning 1 mole of a compound. One is forming 1 mole of a compound. And we talked a little bit about this delta H, enthalpy, and how we can manipulate it. But first, let's go on and talk quickly about tutoring. So tutoring, you can go to this website, or you can just Google, CSUSB tutoring, and you'll get to this website. And here are all the times available for online tutoring. Like everything, it's online. All of these are students that took Chem 216 in the past and did well in it, A's or B's, usually A's. You can see there's times available every day of the week, including weekends and at night, 4 to 9 p.m. or 4 to 8 p.m. On given nights. So you can go ahead and you can get the help that you need. And now this is just a different way, right? You can come to my office hours, go to SI, you can go to this tutor. One thing with this tutoring, it's not specific to the class. So come prepared with questions. What that means is they'll have taken Chem 216 and know the material, but they won't have taken it from me, and they won't be necessarily affiliated with the class. So you can't say, hey, I don't get lesson 3, because they don't either. They're not in the class. So what you have to say is, I don't understand enthalpy. What is it? Why can't we just say heat, right? So come prepared with questions. This is different than SI, obviously. Nimrod knows the material, right? Here's some information on setting up appointments. So you go there and you set it up. All right, so the review questions were about manipulating delta H. So we're given a delta H at the top. A goes to B, and we're said delta H equals 200 kilojoules. Well, what happens if we have half as much? What's going to happen? Well, half A going to half B, my delta H is going to be half as much, 100 kilojoules. What if I reverse this? Instead of A going to B, I have B going to A, right? So my product in the first equation becomes my reactant here. Well, now I'm going to reverse that delta H. It's now going to be negative 200 kilojoules. So this would be exothermic, whereas this one is endothermic. Okay, and then what happens if I reverse it and double it, right? So here, I not only reversed it, I made it by 2. So what I'm going to do is I'm going to do 200. Actually, let's move that because I know what's going to come up. I have 200. And then I reversed it, so I'm going to make this negative, and I doubled it, so times negative 2. So that'll give me negative 400. Okay, so we're going to be doing that a lot today while we go through something called Hess's Law. Hess's Law is named after that scientist, Germain Hess, and it's a very useful law, right? Let's say we have a reaction A plus B goes to C plus D, and we want to know what is the delta H for it. What's its enthalpy change or heat change? Well, we can either do what we talked about last week, which is calorimetry, where we do the experiment in calorimeter, figure out the heat, figure out the number of moles, or we can determine its delta H based on the delta H of other reactions. And this is called Hess's law. Hess's law states that if a reaction can be written as the sum of other reactions, then its delta H is the sum of these reactions. Okay. Let's see what this means, or some of these reactions delta H. Okay, let's see what this means. A goes to C. If I say delta H equals 45 kilojoules, and B going to D, delta H is negative 25 kilojoules. Remember, this not here, this means it is under standard conditions. Okay, so what happens if I sum up these two reactions? Well, A and B are my reactants, so they're going to be reactants here, and C and D are products here, and so they're going to be products. So I'd get A plus B going to C plus D. I could reverse these and say B plus A or D plus C. That doesn't matter. But reactants are reactants, products are products. And notice what happens with my delta H. It goes from, I have 45 kilojoules for this first reaction, negative 25 for the second. I sum up those two reactions, I get 20. This is Hess's law. Now, this is a very simple one. We're going to do some harder ones in a little bit. Okay? All right, so let's say we have this reaction. Oh, by the way, you'll notice here I used A and C and B and D. These are generic reactions, right? We can do it for either generic reactions, there is no element A. That could be any compound. Or I could do it for a specific reaction, right? So let's say I have C, carbon, plus O2 gas going to form CO2 or carbon dioxide. And I want to know the delta H for this. Well, if I were given these two reactions, carbon plus half O2 going to CO, and I figured out its delta H, and then I knew that CO plus half O2 goes to CO2, and I knew its delta H, well, what happens if I add them up? Right? Notice I'd have carbon, and there's no carbon anywhere else. But here, CO is a product, and here's it's a reactant. So those two are going to basically cancel out. Right? And I have half O2 here and half O2 here, both as reactants. So instead, not cancel out, what I'm going to get is I'm going to get one complete O2 out of this. So if I have reactants here, products here, they cancel out. But if I have two reactants, they add up. So I have carbon plus O2 going to CO2. And my delta H would just be the sum of these two. Right? Now, we can think of this as basically this right here is a two-step process. Right? So in green, I'm going from carbon to CO and then from CO to CO2. That's two steps to get to CO2. Or I could do it in a direct process or a one-step process. And the key thing is that the delta H overall is the sum whether I do it in two steps or if I do it in one step. Here's one way to signify this. Let's say I have here H increasing, right? So here's my carbon and oxygen. Here's my CO2. If I go from carbon and oxygen to CO2, I'm getting less delta H. So I have a decrease in my delta H. So this is lower energy, less E. But if I were to do this in 2 steps, I'd go to CO and half O2 in the first step, lose some energy, and then I'd lose the rest going to CO2, right? So the enthalpy change is same for both, 1 or 2 steps. All right, so let's use Hess's law in a little more difficult one, and I'm going to go to the board for this. So let's say we have this reaction here. A plus 2B going to 2C. Or sorry, yeah. And I want to know its delta H. Okay, I'm given some information. And usually what we do is we just label these as 1 and 2 and 3, etc. However many reactions I have. I have 2D going to A plus B. And I know its delta H is negative 200. And I have number 2, which is D plus half B going to C. And here I know that its delta H is negative 50. Remember, these negative signs are very important. Make sure you are careful with whether things are negative or positive. I'm just going to say the numbers, even though they're kilojoules, make sure they're all in the same units, right? Because apples and oranges don't add up, but kilojoules and kilojoules will add up. Okay, so the first thing I should always do is I should look at this, and I need to manipulate these in a way to get to this. And this can be tough, but the first thing you always want to do is you want to look at this, and you want to say, which reactions have A in them? Well, number 1 has A in it. But if I look at B, B is in 1 or 2. And then C is only in 2. So what that means is A or C, those are going to be the things I start with. I always start off with things that are only in one equation. The reason being is, if I wanted to get 2B as a reactant, I could either get 2B as a reactant by changing number 1 or by changing number 2, right? I don't know where to start. But if I want to get A as a reactant, I'm not going to do anything with number 2. I'm only going to use number 1. All right, so let's try to manipulate number 1 to get it 1A as a reactant. All right, so right now I have 1A here. But notice here it's a product. I want it as a reactant. So what do I have to do? I need to take number 1 and I need to flip it. I'm going to put -1, that means flip it. So if I take this and flip it, I get A plus B going to 2D. So I don't get confused. All right. And now A plus B going to 2D, if number 1 is negative 200 kilojoules, then the opposite will be 200 kilojoules. I can then look and I can say I have A in the right place, but I don't have C in the right place, and B is not right, and I have D, which I need to get rid of. So let's now try to get C in the right place. Well, if I look at number 2, I have C as a product here, C as a product here. So that matches off. But notice, I have 2C here and only C here. So what do I have to do to number 2 to get it to be that I have 2C? I need to take it and I need to multiply it by 2. All right, so I can do that. I'll get 2D plus B going to 2C. Okay. And now, if this was -50, I'm going to get -100 kilojoules for that. Now let's add them up. Okay? So I have A plus B, so that's going to give me 2B, plus 2D, goes to form 2D plus 2C. Well, I have 2D going to 2D, so those like they don't exist. Right? So I have A plus 2B going to 2C. Right? I can only cancel both these because they're both 2D. If this was 2D and this was just 1D, I could cancel this and this would just still be 1D. All right, so this is what I wanted to begin with, okay? And I have 200, negative 100. I'm going to get 100. And that's my answer. Okay, let's go ahead and let's look this over. Okay, so the first step always is determine which compounds are in which equations. So for instance, B, we said, was in both equations, whereas A was only in one and C was only in two. So that let me know, hey, I'm going to try to start with the A or C. In the problem I did, I started with trying to do A, but I could have started with equation 2 to get C in the right place. And then I did that. I did my rearrangement, and I got my answer. Be very careful of the signs, okay? And be careful of knowing whether something's a reactant or a product. The last thing, and we'll go through some at the end, notice how I used equation 1, then equation 2. It's not always that case. Sometimes I'll do them in different orders. Sometimes, hint, hint, in a question you'll see soon, you won't even use an equation. Okay, so let's just look at this a little bit in more detail, right? So notice that we did this reaction in 2 steps, right? Well, we can think of what actually is happening here, right? In step 1, we're forming 2D, right? And this has a positive delta H, so that means it gets heated up, right? So here's a representation. I start off with A, and then here's a B, and here's a B, and I form some Ds, whatever reaction that was. And then in step 2, these 2 Ds reacted with the B, and they formed this compound C, right? But now this step was exothermic, right? It was giving off heat. It was negative. So I put heat into it, and then I got heat out. But overall, I put more heat, 4 fire emojis. Here I have 2, right? So I put more heat in than I got out. So that's why my delta H ends up being positive, because I have more I have to put. Okay, so now it's time for you to do a problem. So work through this problem, and it's on the worksheet. Work through it, try to figure it out, and then look at that video. Make sure you try it first. Hess's law, I've said this a lot of times, I know it's annoying, but Hess's law is all about you doing it and you trying. Okay, so let's go ahead and let's go on to another problem. This one a little more tricky, and this one actually with real equations. Okay, so let's say we have this equation up top that we want to get to, and we have these 3 equations that we want to go to. All right, so now I'm going to take a pause real quick, put that up there, and then we'll get back. Okay, so I have these all written up there. While I was doing that, I had a peep, so I have lots of energy now. And it was, one of the chicken ones. I don't like the bunny ones. They're just not as good. And when they have them the rest of the year, it's, they have them like the pumpkins. That's stupid, right? It should only be the chickens and the yellow ones. Those are the only ones I accept. All right, so this is our goal, and this is what we're given. So we want to take these 3 and somehow get to this, right? I won't do it, but you can kind of see, like, I can just add these up, right? I always see that someone who's like, I don't remember it, but it's on a test, I'm going to do it, I'm just going to add these up. No, it's not just adding them up. I have to manipulate them in order to get to that. All right, so what do I do first? I look at this, my goal, and I say, where's N2? N2 is only, it's not in equation 1, it's not in equation 2, it's only in 3. Okay, where's O2? O2 is number 1 or number 3. And N2O5 is only in number 2. All right. Now, what am I going to do here? All right, so now I have 3 equations, and I want to manipulate them to get to an answer. All right, so what I need to do is I'm not going to use O2 as my goal, because if I used O2, I could either get to 502 by manipulating 1 or 3 or some variation of it. That's too confusing. One other thing before I go on, when you do these problems, give yourself space, make sure you have stuff. If you crammed all together, it's like, wait, am I manipulating this or is this what I given? And also it helps to put all the reactants on one side, all the products on the other. So line up all these. That way you don't get confused. Okay, so I can either go with N2 or N2O5. I'm going to, because it's only in 1, I'm going to start with N2O5, right? I could go the other way. Actually, I'm going to start, because I have it in my notes, I'm going to start with the N2. I could start with the N2O5, but I'm going to start with N2. So how do I get to N2 from number 3? Well, this has 1 N2. This has 2. So what I need to do is I need to multiply this by 2. So number 3 times 2, that's going to get us 2N2 plus 6O2 plus 2H2 going to form, let's just see how this looks. All right, I think it looks all right. That's going to form 4HNO3. And seeing that I multiplied all those coefficients by 2, I didn't change any of the compounds themselves. That means I'm going to take this and multiply by 2. That's going to be negative 696.4 kilojoules. And I'm going to include that for completeness. All right, so I got N2 in the right spot. Okay, now O2 and H2, I don't know how to get those, but I know NHNO3, right? That's not in my thing. But now I'm going to try to get N2O5, right? This always reminds me, there used to be this game called Mastermind, where you put pegs in the right spot to get some code, and you kind of said, oh, it's in the right spot, but not, it's the right color, but not in the right spot, and you move it around, right? We're trying to get all of these in the right spot. I have my N2 in the right spot. I now want to get my N2O5 in the right spot. So I can do that by equation 2, right? It's only in equation 2. And notice here, I have 2N2O5 as a product. Here I have 1N2O5 as a reactant. So I'm going to take this and multiply by negative 2. Right? All right, so that's going to get me 4HNO3 going to form 2N2O5 plus 2H2O. 4 and 2 and 2. And seeing that I reverse this, this is now going to become positive. If it was negative, positive. And I'm going to get twice as much. So that's going to be 153.2 kilojoules. So now at this point, sometimes you can tell what the next step is. I always say after each one, you should add them up. Okay? So I'm going to add these 2 up. Notice I have HNO3 here and HNO3 here. 4 and 4. So those cancel out. So now I get 2N2 plus O2 plus 2H2. There are no other reactants. Goes to form 2N2O5 plus 2H2O. Right? I look at all my products, there are only two. I look at all my reactants there. If there was something here, that'd go on as a reactant. Okay, so that's adding all those up. I also add up these. So it's going to get me negative 543.2 kilojoules. Okay, so I'm going to pause it one more time, eat another peep, and put this up, and that'll give me some room to work with. All right. All right, and so we're back. I just moved what was down here up to here. Notice I put 2N2O5 plus 2H2O. I put this on a separate line just because it was getting too long. That's fine. It's still a product. I just put it on another line. That sometimes happens when we get these really long equations. All right, or reactions, I should say. And that had that as my delta H. All right, so now I look at this and I compare it to this. And I have N2 in the right spot, in the right amount. I have O2, but I have too much. I have this H2, which I need to get rid of. And the N2O5 is in the right spot, but I still have this H2O, right? And this reaction is not the same as this. Even though it has some, it's pretty close. It's not quite there. And so now what I need to do is I need to go ahead and I need to try to get rid of some of this stuff. All right, so now here's where I look at, I've used number 3, I've used number 2. So can I use number 1 to help me get rid of some of this extra stuff? All right, so let's look at this. I have 2H2O here as a product. If I want to get rid of that, what do I have to do? I need to add H2O as a reactant. If I add two H2Os, those are going to cancel out. So how do I take number 1 and get it so H2O is a reactant? Well, I flip it. And I also have to multiply by 2. So when I do that, I get 2H2O, goes to form 2H2, and then half O2 times 2 will give me just O2. And this is going to have a delta H, half this, but also negative. Or no, sorry, twice as much. And it was negative, now it'll be positive. So it'll be positive 571.6 kilojoules. So now I have these two, I can add them up, and let's see what we get. All right, 2H2O, 2H2O, those cancel out. As expected, 2H2 here is a reactant. Product here, cancel out. And notice, I have 6O2, 1O2. So what's going to happen is this is going to cancel out, and this 6 becomes 5. Why? Because if I give you $6, you give me $1, I'm going to end up with $5, right? So it doesn't matter that you're giving me that dollar back. It could just be the same as, hey, I'll give you $5. Okay, so I have this. Let's write it down one more time. So I have 2N2 plus 5O2 going to form 2N2O5. That's what I wanted to begin with. So I can just add these two up, and I'll get 28.4. Okay. So even though, right, so I end up with 28.4 kilojoules. Right? If it still wasn't there, well, now I could use a fourth equation, right? If I was given a fourth, or a fifth equation. You know, you could do Hess's law problems where there are 20 equations. Typically, the longest you'll see in this class is 3, maybe 4 or 5, but nothing long. Let's go ahead and let's look at this on paper. Okay, so we started off by, or on screen, I should say, we started off by saying, okay, what is where, right? Only equation 3 for N2, only equation 2 for N2O5, O2 is in 2, right? So I go through, I manipulated the first two, first equation 3, then equation 2, and then I use number 1, right? And then once I sum them up, I get my final answer. Okay, here's a key. Notice how I used each equation once, okay? That should be how this works. You'll either do each equation once, or sometimes there'll be a superfluous extra equation you don't even use. But if you end up having to use the equation a second time, it's like, oh, now I need to use equation 3 again. Now I need to use equation 1 again. You probably did something wrong, okay? So go back, see where you did wrong. Usually, sometimes what happens is you wrote it down at the very beginning wrong, or you multiplied something wrong, right? So make sure, check every step to see if you got it right. Okay, so now here's another problem that you can do. This is a problem, again, with real life examples, real life compounds. So you're going to try to find this, right, reaction from these 3 down here, okay? By the way, notice how I called this delta HF. The reason being is this reaction on top, strontium carbonate, right? This is the reaction for forming it from its constituent elements in their natural state, right? Strontium is a solid, carbon is a solid, and O2 is a gas. If you're having trouble remembering delta HF, go back to lesson number 3 and look that over, because we're actually going to use it in a little bit too. All right, we're actually on the next slide. Okay, so you'll do this problem, come back, right? Now let's do one other thing with Hess's law. So Hess's law is really convenient because if I know all these reactions, I can do it, right? Well, it turns out that what if we want to know delta H for a reaction, reactants going to products? Well, what if I figure out the delta H to take these reactants and turn them all into just elements, and then somehow I took all those elements and I put them back into products, right? This would be using delta HFs, right? Heats of formation or enthalpies of formation, okay? So what we can say is that the standard enthalpy change for any reaction, delta H, is equal to the sum of delta HFs for the products minus the sum of delta HFs for the reactants, okay? We'll go through and we'll do a problem, then we'll explain why it works in a little bit. But one way to look at this is delta H for any reaction is equal to the sum, that's this symbol right here, of all the delta HFs for the products. But notice I have to use their stoichiometric coefficients. Remember, that's the coefficient in front of the compound. And then minus the sum of the heats of formation for the reactant. Okay? We'll look at this in 1 second. Okay, so it's products minus reactants. All right, so let's do this problem. So we're asked to determine delta H naught, the standard heat of formation or standard enthalpy change for the reaction 2MnO solid plus O2 going to form 2MnO2 solid. Right? And we're given no equations. We're just told, hey, use their heats of formation. Well, we can go to the book. Boy, it's right here. And Appendix G, which is in the back of the book, right? It has the standard thermodynamic properties for selected substances. Boy, let's look at that. So if I look at the back of the book, I'm going to do that right now. I'm going to click on this link, and I'm going to go to it, right? You can just use the link you've been using the entire time to look at the book. And when I look at it, I see something that looks like this. I can go down, I can look at the table of contents. I can scroll down. So we're in chapter 5 now. I can go all the way to the bottom. And I said Appendix G, right? Standard thermodynamic properties for selected substances. And when I do this, I see a whole bunch of substances, right? They're alphabetical by the first element or the main element. So for instance, we have aluminum, and we have aluminum solid, aluminum gas, etc. More complex. Here's that delta HF. Here are other things that we'll explain in a little bit or in a few class periods. All right, so I can go through here and I can find what I'm looking for. All right, so what did we want to look for? We wanted to look for MnO solid. So I can go down, I'm going to look for manganese. Okay, let's bring that up one more time. MnO solid, right? Okay, here it is. It's negative 385.2. If I looked at the top of it, it's in kilojoules per mole. All right, so I'm going to do this for the rest of them, right? On problems, you'll have to do this yourself. All right, so here's that manganese oxide. I do the same thing for O2. It's actually 0 kilojoules per mole. The reason being is this is a standard state, right? O2 from O2, we went through this last time. And then MnO2 is negative 520.03 kilojoules per mole. I looked this up. It was right underneath the other. All right, so now what I can do is I can just use these in order to figure out delta H for that reaction. All right, let me just put this on the board. So I want to figure out delta H, so I use my products minus my reactants. All right, so what are my products in this case? It's MnO2. So I have 2 of those. So I do 2 times 520, or negative 520.03. And then I subtract 2 times negative 385.2 plus, right, 0. That's for the O2. Okay? Notice how I put parentheses in, because it's minus this term plus minus and minus this term. Okay? Be very careful with that. In this case, it doesn't matter because this is 0, but on the problem you guys will do, it will. So I go 2 times this, gives me negative 1040.06. Okay. Now I go ahead and I do the same thing for this. It would be minus 770.4. Okay. And then this is 0. This would be negative 1040.06 plus 770.4. And so that's going to give me negative 269.7 kilojoules. One thing to note is, while these are all kilojoules per mole, because I'm multiplying by moles, this ends up being kilojoules. All right, so let's look at this one more time. So I look up all these values in Appendix G. I use this, and I start with my products. Right here, this is my MnO2 minus my reactants. And then I just Be very careful of the signs, and I get my answer. All right, so here's why does this work? Well, this isn't as important, but I would like to show that I'm just not taking this and I'm not just making it up, right? The Easter Bunny didn't deliver it, and I go, all right, this actually is based on Hess's law, right? Why? Because, remember, delta HF for MnO2 is based on this equation here, right? I take MnO2, I make it from manganese and from O2. I have its delta H. If I were to do this times 2, I would get this equation right here. And it would be negative 1040.06 kilojoules. If I do the same thing for MnO, sorry, this was for MnO2, right, the products. If I did the same thing with MnO, I would have this equation, right? If I multiply that by negative 2, because it's a reactant, right, I would get 2MnO goes to 2Mn plus O2, and it'd be 770.4 kilojoules. And if I add these two up, right, I would get this long equation, but notice there's two O2s here, there's only one here, so this would cancel out, and I'd end up with 1 O2 plus 2 MnO going to form 2 MnO2, right? And I can figure out my delta, right? So this equation right up here is a convenient way to figure out enthalpies of enthalpies for reactions based on heats of formation. All right, so why don't you guys, let's do one more problem. Let's say we had this problem here. We want to figure out delta H for this reaction right here. I already looked up those delta HFs, right? So I can go ahead and I can do the products. That's that negative 814. And I did minus 296.8 plus 2 times 39. And I was very careful to use these signs correctly, right? So I'll multiply these together, add that to that, and I get negative 595.2 kilojoules. Okay? Be very careful of signs. Notice I didn't multiply 814 by anything because there's no coefficient in front of here. I didn't multiply this 296.8, negative 296.8 by anything because this is a 1. But I did have to multiply the OH by 2 because of that coefficient. Okay, so why don't you guys do a video problem, right? Go ahead, break out that book or look online, get those appendix, get those delta H's and figure this out. All right, so that is it for Hess's law, right? Hess's law is really an important law. We'll use it a lot. It's very convenient because it allows you to do really complex equations based on smaller equations. Okay, a reminder about Zoom SI tutoring, this week's schedule and next week's schedule, and then April 27th, which is 2 weeks away from when I'm recording this, and 1 week away from when some of you are watching it, the test. Okay. All right, one last thing, the homework for this lecture or this lesson is due via Blackboard. It's due 4/20 at 11:59 p.m. So you're going to go on to Blackboard homework on the website. You're going to go ahead and click on that and you see homework number 4. When you go through there, it gives you some things. It tells you about problem 1 through 2 and then problem 3. Okay. You're going to go ahead, do number 1 and 2. These are fill in your answer. You just type it in, no units. Number 3, you actually have to attach a file to. You're going to take a blank sheet and you're going to work out that problem and you're going to attach it. I don't need to see all this stuff. I just need to see how you worked it out in your final answer. Make sure it has your name at the top, how you work through each one of the steps, and then circle your final answer. What you're going to do is you're going to either scan or take a picture of it, upload it to your desktop or directly into Blackboard, and you're going to submit it, right? You're going to use this button right here to submit. Okay? All right, you have time to do this, so don't wait until 11 p.m. on 4/20 to try to do this. Do it before. Something doesn't work out, figure it out. And talk to me in office. All right, see you guys next time. Enjoy your week and enjoy any candy you have left over. All right, bye.